Wait a minute.
I wait. Okay, we record. Hello, everybody. Welcome. Today we have talking David Lagziel, Dudu Lagziel. David Lagziel is a professor at Ben Gurion University of the Negev. He did his PhD under the supervision of Professor Ehud Lehrer. Dudu excels in everything he does, besides guessing election results. His optimism is biasing him there. He's routinely awarded any teaching excellency prize. His research won the Mashler Prize and an ISF grant, and he's the youngest organizer of the Israeli Game Theory Conference. All the above is done while being the proud father of 4 young children. So, Dudu, stage is yours.
Thank you. Actually, I'm really very bad at guessing results, but last time I actually diverted for my previous guess, and it seems that it goes also the other way around. So I'm guessing I'm a jinx. Thank you very much for the invitation. This is a great opportunity to talk to the game theory community, and I'm going to present a joint work with Ehud. We've been working on this for 3.5 years now. So this is a combination of 3 papers. One was published 2 years ago at the AR Insights. The second one is forthcoming at AJ Micro, and we'll be starting to circulate the third in about a few weeks. I'm hoping in about 2 weeks. The general idea is screening. Okay, so we take a very broad perspective, sorry, on the topic of screening. Basically, you can think about screening job applicants, investment strategies, research papers. We actually provide a nice example in the first paper about an editor that tries to screen papers based on noisy assessments. These 3 papers, the talk will be divided into 3 parts. And I'm mostly excited about the last one because basically it's the recent one and nobody cares about the past work. So I'm going to focus on the last one. I'm going to brief through number 1 and number 2, present main results, but focus on number 3. So there are a lot of examples, and the model itself, the fact that I can join all these papers due to the fact that the models are rather simple. Basically, we have 2 random variables and a number. Okay, so it's a very simple model. And the main goal of our decision maker, she gets noisy evaluation, noisy assessments, and she tries to maximize the expected value of accepted elements. Then you get noisy evaluation and you decide whether to accept or reject. And ex post, you evaluate your decision, the ex post distribution, and you observe the expected value. The key questions that will follow each part of the talk. So we have 3 questions, each for one part of the talk. Starting with the first, our original question was whether being more restrictive in terms of screening can be beneficial, is always beneficial, basically. That was the basic question. It turns out that not so much. I mean, it could be beneficial, but it could go the other way. So that's the idea behind the bias of screening. The second part of the talk, the second paper, focuses on how can we compare, how can we characterize the superiority of one screening process over another. I mean, basically, we're trying to evaluate which process is more, which noise is more informative when concerning screening. And we have a notion related to some contraction mapping. I'm going to elaborate during the second part. And the third one, the most recent paper talks about sequential screening. And in that paper, we ask whether when and how should we add stages to a screening process. So whether it's beneficial to add more stages or not, This is the one we've been working on for most of the times throughout this 3.5 years because of the pandemic and because we were stuck. Actually, the pandemic might have helped because we had to let this one go and we started thinking in different directions. And then we got back and we saw that we were wrong the whole time and everything progressed from there. So I'm going to provide a very brief literature review because basically these are still 3 papers. The first one on biopsy screening is mostly connected to the Milgram work and the most recent paper by Chambers and Healy. I should be clear that we weren't aware of the Chambers and Healy paper, and we became aware of that only because of a follow-up paper that was recently published in JET that connected our work to theirs. So we apologize for not referring to that paper in our work. And for the second paper, what we're doing is mostly connected to the work of Lehman in 1988 and the more recent econometrica paper from 2009. But our focus on screening actually enables us to provide more insights and augment their results. And the sequential screening paper, you can relate it to the Condorcet-Jury theorem. Actually, I discussed this with Elon, I think, a few months back, and he provided this angle, and also to the Lagziel JP paper about the Peter principle. Okay, but we're still thinking about the exact positioning of this paper. Okay, so I usually like to start with an example, but I'm gonna apologize. I'm keeping the example for the third paper, for the third part. Okay, so I'm gonna brief to the 1 and 2. I'm gonna keep the example, nice example for the third part. Our basic model, as I already said, we have 2 random variables and a number. Okay, so a screening problem. What's a screening problem? Is we relate to it. We have V, that's an input variable. These are basically the values in question, the intrinsic values we are trying to find out when examining elements. N is a noise variable. And we have some specification. V is non-atomic, convex support, and it is bounded. In most cases, we think of bounded random variables. And N is a noise variable, symmetric around 0 and independent of V. So the decision problem is basically the decision maker observes V plus N, so the actual values plus the noise, and based on that decides whether to accept or reject. Okay, so this is the V plus N. Now there is a capacity constraint. The capacity constraint dictates that the decision maker needs to accept portion P of the elements. Okay, so you can see this over here. Okay, so the main goal of the decision maker is to maximize the expected value of V, conditioning on given this capacity constraint. Any questions regarding the model? Okay. So most of the talk and most of the papers are, we use threshold strategies. The reason we do that is first of all, in the absence of noise, they are optimal. Okay, so this is basically trivial. They are simple strategies. They don't seem to be rather biased. You don't distort. They seem normal in some sense. And basically they are commonly used when we screen applicants for students. When we screen students for a bachelor's degree or a master's degree, we use threshold strategies. And almost, I think all academic institutions do that. So just to, and in the second paper, we actually differ from threshold strategy to some extent and discuss optimal ones. So just in terms of notation, when I'm going to use this pi hat, this couple pi hat, it means that I'm observing the expected value of V, so given a screening problem, conditional on using a threshold value of B. Okay, so this is the expected value of V, conditional on V plus N greater than B. Okay, so now I can provide the basic definition of a screening bias for the first part and the main results. What's a screening bias? So basically, a screening bias, you take a random variable V, the input variable, and we say that it has a screening bias if you can generate a noise such that the expected value is non-monotonic with respect to the threshold value. The expected value of B is non-monotonic with respect to B, the threshold value. Okay, so I'm going to move back just one slide. If this function basically is non-monotonic, we say that there's a screening bias, okay? Or you can use a different terminology. You can generate a bias by, if you increase B, you might go up and some down and up and down. You have this some sort of oscillation motion. That's a basic screening bias. That's just a screening bias. And we say that there's an extreme screening bias if you can make these jumps. It could be very or extremely non-monotonic. Basically, you can take two values, B1 and B2, and while increasing the threshold, you have a very massive jump. So with using B1, that's the low threshold, you get almost an optimal outcome, almost an optimal one. Okay, so that's the V cap, that's the upper bound on V. So an extreme screening bias means that for every epsilon, you can generate a noise in two caps, two thresholds, such that with the lower one, you get almost optimal results. And with a slightly higher one, you get as if there's no screening whatsoever, meaning basically that the jump, once increasing the threshold, the jump is rather extreme. And our first result basically indicates that for every input variable, and recall it's bounded, non-atomic, and so on, every input variable has a screening biases. Okay, so this is the focus of the first paper. You can take any random variable, you can generate a noise. Actually, the noise, what's important is that you have black swans. You have this very large deviation with small probabilities, and that will generate biases. Okay, because if you have massive jumps with small probabilities, then the expected value is a non-monotonic function. Okay, and that's not very difficult to prove. And you can start, and most of the paper actually tries to elaborate on how robust you can take this result to be. Okay, and you can basically extend this to, you can make the noise be non-atomic with a normal-like form as this. And you can also, you can extend this in various ways. I mean, you get this jumps a lot, even if you take atomic random variables, you can still get these results. The basic intuition is the fact that the noise, although the noise might be slim, it could still generate ordinal changes in these values when you're doing a screening. So basically, you get this non-monotonic option. Any questions about that? Okay, so basically, we're done with the first part. As I assured, I'm gonna provide only the main insights from the first two papers. So this is the first one. And now moving on to the second one, our original motivation was, well, we have these biases. Are there any ways that we can correct the process? Meaning, is there some way that we can adjust the process to eliminate the bias? And that got us to thinking, well, do we know anything about whether one noise is better than another? I mean, what do we know about this question? Whether you have two noises, would one be better than another? If you're trying to adjust the screening process, basically you're trying to adjust noise, or you're trying to determine which noise is better. So the focus of the second paper is how to compare two sources of noise. And again, we start off with something that at first glance, it doesn't seem too obvious, but after we go through the details, you understand the motivation. And we start with the definition, which is a noisy amplification. Basically, it means that you just add a noise, add independent noise. N2, I'm going to go through the definition. N2 is a noisy amplification of N1 if N2 is distributed according to N1 plus some independent random variable N3. Okay, so this is noise amplification. Why do we focus on this definition? Because the first thing we wanted to prove was that adding a noise could not improve a process, a screening process. Okay, so we've spent a couple of weeks on that in order to reach the conclusion that that's not true. And adding a noise can improve a process. Okay, and at first glance, maybe it's not intuitive, but basically it's not that of a big deal. So the first more anecdotal result states that for every input variable V and for every capacity P, you can always generate two noise variables, N1 and N2. One is a noisy amplification, N2 is a noisy amplification of N1, but screening according to a screening problem with N2 generates better results than N1. Okay, so basically, and in the proof in the paper itself, the added noise is just a coin toss. So we call this just a lucky coin. Okay, as if you can generate lucky coins, as if taking N1, adding some binary coin and binary noise, and you get better results in terms of screening. Okay, but I don't think that, well, it's nice to fix ideas regarding that, but the main motivation is that say you have a noise that's plus and minus half with equal probabilities. If you add an independent noise of plus and minus half, again with equal probabilities, with a probability of half, you get the accurate evaluation. So in this sense, you have some correction. Okay, although it distorts, you have some distortion, you still have, it can correct to some extent the noise, the original noise. And this is why you get this phenomenon. Okay, but just a basic idea so we can progress. And as I stated, our main motivation was, okay, so adding noise, we don't know whether adding noise would help, but what we want to do is determine whether one source of noise is better than another. So we introduced a basic definition of screening dominance, and we say take two noise variables, and just to simplify what I'm going to say next, we're assuming you have continuous densities. So these are non-atomic, convex support, random variables, and you have positive densities. And we say that one random variable N1 dominates N2 under threshold strategies if for every V and P you get better results according to N1 with a weak inequality, and for some cases you have it with a strong inequality. And what we want to do is to characterize this this concept, and for that I need to introduce a certain mapping between N1 and N2. So the PT mapping, the percentile translation mapping, you can also think about it as a quantile translation mapping. Basically means that you take the percentiles of one variable and you map it to the percentiles of the other. Okay, so this David? Is the, yes.
David, I'm sorry for interrupting. Would you mind me asking a question about the definition, the first definition here? So P is the capacity, right? It's not the threshold, is it?
It's the capacity, exactly, yes.
And sigma hat, how is it quantified? Is it a fixed threshold strategy, or are we supposed to?
So SP itself is basically the triplet VN1 and P in this case, and VN2 and P in that case. So for every VN1 and P, you have a specific threshold to sustain the capacity of P. So the threshold is determined with respect to P. Basically, the sigma hat is a function of Vn and P.
Okay. Okay, thanks. Yes, okay, thank you.
The mapping is basically you take the CDF of one variable, you take the inverse, and you combine the two, and you get a translation from the quantiles of one variable to another. And we, assuming that the derivative is less than 1, in this case, we say that N1 is a contraction of N2, and the motivation is not complicated. Basically, in some way, it means that N1 is more dense than N2. It means when you translate the percentiles, they are getting closer, not necessarily strictly closer, but in some cases they are getting closer in the support of N2. And our first main result in this paper basically states that the screening dominance under threshold strategy and the contraction mapping are actually equivalent. So this is the first equivalence result. So N1 dominates in terms of screening N2 under threshold strategy if and only if N1 is a contraction of N2. Okay, meaning if it's denser than N2. Okay, and this is I should say upfront, this is a characterization. Under threshold strategies, we do not have a general characterization, only a partial one when we go to optimal strategies, general strategies. Some graphic motivation about the proof. How do we prove this? So again, it's not really complicated, but you need to pay attention to the details. You start off with this is a threshold screenings, and V and N2 are independent. So you have this this figure on the left, and you're using some threshold, and you're taking everything above it. Okay, so V and N2, you take everything above L2, and now you can take L2 and translate it to terms of N1 using the mapping itself. So this is what you have on the right with this L2 here. Okay, and now because the slope is greater than -1, then basically you're trading off. When you compare the two screening processes, you basically trading off this A and B areas. Okay, because with the L2, you're getting this dark gray and white, and with L1, screening according to N1, you get this light gray and dark gray. So basically, you don't only have better expected result, you actually have first order stochastic dominance when reverting from this to the other. What happens if we divert from non-threshold strategies? Basically, it gets complicated. Okay, this is a very simple example to illustrate it. So take everything to be binary atomic. Okay, so N1 is ±1 with equal probabilities. N2 is ±2 with equal probabilities, and V is 0 or 2 with equal probabilities. Okay, so now you get signals. You take V plus N1, and basically you get only 3 signals, because you have 0 and 2, and you add plus minus 1. So you either get a 0 minus 1, or 1 or 3. So 1 is very ambiguous, okay, because you can get 1, you can get a signal of 1 if you have 0 plus 1 or 2 minus 1, and both will generate a signal of 1. However, you don't get this phenomenon when you take N2, that's plus and minus 2. Okay, so you don't have this ambiguity. Although N1 is a contraction of N2, in some standard form, just divided N2 by 2. So what we stated previously does not hold when we talk about non-threshold strategies. Okay, so let's discuss optimal strategies. What happens under optimal strategies? So basic definition, N1 S dominates N2 without the restriction to threshold strategies. If you get better expected results under a screening with respect to N1 than under a screening with respect to N2, and the inequality is strict for some V and P. Okay, and the pi star is the maximal expected value. Now, reverting from threshold strategies actually helps, because in this case, if N2 is a noisy amplification of N1, meaning you take N1 and you add noise and you get N2, then it's inferior. Basically, N1 is better than N2 in terms of screening. So the basic intuition that adding a noise can't help, you can actually restore it when you revert from threshold strategies to optimal strategies. Okay, so adding a noise using optimal strategies cannot help. And we can use this in order to provide some partial characterization if you consider only normally distributed noises. Why normally distributed noises? With a 0 mean, because it's symmetric on 0. Because this set is closed under addition, and now you have equivalence between noisy amplification and screening dominance. So the two are equivalent to one another, assuming you only consider normally distributed noises. Again, I'm not going to get into all the details, but I should clarify that the question regarding a full characterization is still open. So basically, we don't have a full characterization for screening dominance under optimal strategies. Okay, and we have an example showing that a noisy amplification is not enough, meaning you cannot characterize screening dominance with noisy amplification, and we have a very simple example for that. Questions?
You mentioned how is it related to Blackwell?
So the basic idea of a garbling is in some way related to ours. So basically, in Blackwell, you have this the basic notion of garbling. In some way, this relates to ours by the fact that you can add noise. The fact that you're adding noise and you're not improving a process, you're only damaging it. Okay, but this is the way it relates to Blackwell, nothing more than that.
So it's not related directly to garbling. Although being denser, I mean the notion of being denser, that sounds like garbling in some sense.
Maybe, but we don't relate that to garbling, but might be. I mean,
and it's not, and you don't use linear programming here.
No, actually, we prove everything from scratch.
It's not convexity. It's unlike Blackwell.
No.
Okay.
Okay, so all in all, we adjourn now at part 1 and part 2, and now we can start discussing number 3, the third part of the talk. This is about sequential screening. Okay, so what's the idea? Well, assuming you have an academic position or you ever been subjected to the screening process, or maybe work outside academia, you know what sequential screening means. Basically, you send out CVs, and then only part of these, you get a lot of CVs if you're in the recruiting committee, and only part of them goes through the next stage. And then there are interviews, and only a subset of the ones that are being interviewed are going forward to flyouts and so on. So this is the basic motivation to sequential screening. Basically, we say, okay, so you have this distribution of values, that's V, and we denote by V1, so that's the first stage. And now you can filter out elements and reevaluate independently the ones that are left. And you can do this repeatedly. And our main question is whether it's beneficial or not. Okay, because everyone are doing sequential screening. Basically, if you have, when you send out academic papers, you have sequential screening. Okay, and you actually have multiple forms of sequential screening. I'm going to relate to this in a minute. So the basic framework is you have V, and we denote by V1, so the first stage, and you have, let's say, K screening stages. You have N random, K random variables, independent, non-atomic, convex support. And we only focus on threshold strategies. And in this case, as strategy, threshold values, maybe it'd be better to say. And a strategy is basically a vector of threshold values. So how this evolves, basically you have K stages. The decision maker observes in stage I, she observes VI plus NI, and then fixes the threshold TI and eliminate everything below it, take everything above it. This is how we redefine the distribution for the next stage. And in every stage, you have some capacity PI that's left. And overall, everything should add up to a general capacity constraint of P. Now, I should point out this P is important for our results. Okay, so having a capacity constraint is really crucial for our results, at least for the first part. And we refer to this process as a K-stage screening. Now, maybe one comment before. Now, in the first two parts of the presentation, most of the results stated that if V is something, then you can generate some N to do so and so. Okay. Now, in this work, we have a different approach. Basically, what most of the result would say that for every V and for every N, you get this and that. Okay. So in some sense, this paper provides a much more robust, stronger result than the previous two. What else? So key questions. First of all, the more the better. Is it better to use more stages? Okay. Okay. So now, since we have time, I can tell you that, well, we started off this about a year ago. We started the project, and we were at a dead end because we were trying systematically to prove that if you add a stage, it can only be beneficial. Okay. And it seems reasonable that you can always add a stage and get better results. And then the Corona hit, we weren't able to proceed. And once we got back to it, we took a different approach and eventually reached the conclusion that what we tried to do was wrong. Okay, so basically our basic intuition was wrong. You can actually, there's a very strong argument to make that adding a stage could be very bad for a screening process. That adding a stage could be really quite bad for screening. And in general, I should say that you can, the entire result, you can also provide a different framing. Instead of using, let's take the academic example. Instead of using one referee for a paper, you can say, should I use one referee or two? So would I get better result using two referees instead of one? Okay, so this is the alternative formulation. Basically, it's in terms of the mathematics, they're the same. So let's start with the example. Joe, a friend of mine actually. Joe is a team leader in some some tech company, and he's recruiting employees. And let's take the input variable and say that this is the applicant suitability for a job. Let's take it to be uniformly distributed between 0 and 1. Okay. Now, noisy evaluation. Joe has a noise of plus minus uniformly distributed between -1/4 and 1/4. And there's an overall acceptance rate, a capacity constraint of 5%. Okay. So this is the original case. Joe is screening employees for his team, has an acceptance rate of 5%, and you have a noise. Now, one day, the company decides to, I use the term, elevate its screening process. Well, what does it mean? Now we want another interview. Okay, we're adding an interview with the CDO. Okay, and the CDO, he has or she has better screening abilities. So a denser noise, uniformly distributed between -1/4 to 1/5 to 1/5. But unfortunately, she has less time. So what you need to do is first, Joe provides a short list of the top 10%. And then it moves on to the CDO, and in the interview, she eliminates half to get the needed 5%. This is the example, okay? And basically we're asking, was that beneficial for the firm? I mean, adding another interview with a more skilled screener, a more skilled decision maker. And the answer is no, it was not beneficial. Okay, so now I'm giving you two graphs. These are the posterior distributions after screening. So let's start with this one on the left. You have two lines. This is the acceptance rate of 5%. So the blue line is when Joe screens alone. Okay, he's performing a screening, only 5%. And you get this distribution, start off with 0.78. Okay, so it's not bad. I mean, seems quite good. If you take the expected value, you get a decent result. This if you perform the two-stage screening with the CDO, you get the dashed red line. That's this line over here, and it's difficult to see. I know they are rather close. You don't have stochastic dominance in this case, but once you take this and compute the expected value, the one-stage screening outperforms the two-stage screening. Basically, adding a stage wasn't beneficial at all. Now, you can adjust this example, and instead of 5%, take 3%. Okay, just 3, meaning Joe is leaving out a short list of 6%, and then the CDO screens out half. Okay, in this case, you actually do get first order stochastic dominance of one stage screening over 2, meaning adding a stage with a more skilled interviewer generate really inferior results in terms of stochastic dominance. Okay, and the nice thing about this is the fact that you can generate this result for every V, every N, as long as you focus on elite screening. If you're screening at the top of the distribution, really focusing on the elite of the elite, you probably we would get this result, and I'm going to provide the intuition. Once you see that, it's not that surprising, but it's much more robust than previous results. Also, in the paper, in the working paper, we provide the academic angle of using the same 2 team leaders instead of 1. So basically using 1 referee instead of comparing 1 referee with 2, where the 2 follow the same strategy and they are subjected to the same noise. Basically, you just take 2 referees, same ones, have the same abilities, and you perform the same screening. Okay, and in that case, at 5%, 1 referee is better, and everything below 4.9%, you get the first order stochastic dominance of 1 referee over 2. Okay, so once they have the same abilities, the outcome actually becomes more distinct, and at 4.9% and below, you get stochastic dominance of 1 over 2. Why is that? So that's, first of all, the statement itself. So take any 2 variables, V and N, any 2 variables, and there exists P0, a value, a capacity, such that for every capacity below it, 1 state screening will stochastically dominate 2 state screening once you use the same noise and the same threshold value. Okay, and bear in mind the nice thing about this holds for every V and for every N. Okay, again, under the general condition, they are bounded, context support, and so on and so forth. And we extend this result to using different noises, but in that case, once you use these different noises, there are caveats, because we recall what we had in the second paper, because if you have N1 and N2, and N2 is a contraction, you could not have that all the screening is done under N2, because that way you get better results. If you were doing a 2-stage screening and basically not screening anything in the first stage and only screening in the second stage. So that's somewhat cheating. So we don't allow that, but under some restrictions on how much you can use the second stage, basically what we get is that 1 stage is better, as long as you're focusing at the top. If P is quite large, meaning you're trying to eliminate the bottom, only rather in the bottom than below like 80%, you're trying to take the superior 80%, then the result actually reverses.
So the capacity in the second, in the 2-stage process is the same capacity as in the first one? I don't understand.
Yes, we fix the overall capacity to P, but in the 2-stage, you need to be very accurate, because you can basically make an argument that if you have 2 stages and in the second stage the noise is narrower, just don't do nothing in the first stage and screen everything in the second stage. Yeah. Okay, so, and that way you get better results, but this is what I say, it's like kind of like cheating, because you're basically you're converting the 2 stage to 1 stage.
But why is it forbidden even in your theorem? It's not.
So in this case, yes, because we're using okay, maybe missing a word, a stationary fixed strategy, meaning you're using the same threshold.
Yeah. Okay.
Okay, so that's important. Yeah. It's a fixed threshold, meaning you're using the same threshold for both stages. However, we have the next
root of P.
Sorry?
So square root of P.
No. This is a fixed capacity. A fixed threshold means you're using the actual same test. Everyone above 0.7 is accepted. Okay.
Okay.
And we extend this. Actually, we have this extension talking about using the same capacity, maybe different noises, but not allowing going to the extreme. What's the intuition? Because the intuition is what's important in this case. Once you add a stage, and I'm very accurate in this case. Once you add one stage, I'm not talking about a lot of stages, because in a lot of stages, everything reverses. If you add a stage, then you have to allow to more wiggle room in the first one, in the preliminary stage, meaning you have to decrease the threshold of the first stage. If you're running from 1 to 2, then you have to decrease the threshold. In this case, you have to allow some slack into the system. Basically, you're introducing some suboptimal elements. Now, in the second stage, you have a smaller sample. Okay, but by definition, because you screened out elements, you have a smaller sample. Now the noise becomes more dominant, more destructive. So basically, and that's the same thing of using 2 referees instead of 1. That's the same argument. Whenever you're using 2 referees instead of 1, you must allow to some wiggle room in order to sustain the capacity constraint. So basically, everybody should decrease their threshold values, and now there's some miscoordination, and this is why you get this suboptimal result, because you're introducing noise to a very small sample, and this is a built-in element in the system. I mean, you cannot bypass it. It's not a feature, it's a bug, basically, of using multiple referees or multiple stages. You have to go through it. However, if in the second stage you have very accurate assessments, then it doesn't necessarily mean that you get worse results. Okay, but again, so in the paper we extend this in various ways, and I should state that if now you're taking a different approach when P is close to 1 and you're taking capacities above P, then the dominance reverses, and we have this result, the same as the theorem stated here above. If P is there's a P0 such that if P is greater than P0, 2-stage fixed threshold dominates 1 stage. And this actually also explains the next result, and almost the final one I'm going to provide in this talk. So let me say just a couple of words. You might be thinking, well, this guy from Beersheba is telling me that everybody got this thing wrong. I mean, is he telling us that, because you have high-tech companies, you have academic institutions, you have private sectors, everyone are doing sequential screening. So is he telling us everything is backwards? And the answer is no, we're not saying that. Actually, there is a very important distinction to be made when you compare 1 and 2 stages and 1 and, let's say, 20 stages, because they are not the same thing. Okay, sequential screening is actually very good. So in order to present this result, we define what is a perfect screening. Perfect screening is basically a result, an outcome. A perfect screening is a value you get if you were to perform a screening without any noise whatsoever under a capacity constraint of P. Meaning you don't have any noise, you just take the top P percent of the distribution. Okay, so that's a perfect screening. And the second main theorem states that if K tends to infinity, then the optimal K-state screening leads to perfect screening. Okay, so you're taking 10, 20 stages or 10 stages, and you're performing a screening, and as long as you add stages, you're getting closer and closer to a perfect screening overall.
But not monotonically.
Sorry?
Not monotonically.
No, not monotonically, but there are subtleties in this case, so I should clarify it. Obviously, not monotonically. Why does this happen? Okay, so if you're doing one stage instead of 2, and so basically in the 2 stage, you don't have the ability to screen very slowly. So the capacities are quite close to P when you're doing 2 stages. However, if you're doing 20 stages, now you have the ability to start screening very slowly. You're taking the lower, only the lowers of the distribution, and you start eliminating them. And then in the next stage, you're eliminating some more from the bottom. And in this case, basically what you're doing is using a high P's, the high capacities at every stage. However, when you take all of them together, you get a very small P. Okay, because once you take the product of all these capacities, you get a very small value. So the idea is that if you were to perform a very prolonged screening process, then it's better to systematically screen out slowly, okay, only from the bottom of the distribution, and eventually converge to the required capacity. It's not only in existence. We provide 2 strategies to sustain this result, 2 stationary strategies. So you can use a fixed capacity strategy, meaning fixing P to the power of 1 over K in each of the K stages. And you can also use a fixed threshold strategy, a stationary strategy, using the same threshold over and over. Okay, and both of these converge eventually to perfect screening as K tends to infinity. Okay. To summarize, I talked about the first paper, bias of screening. The second paper where we compare 2 sources of noise and relate screening under threshold strategy to a contraction mapping. And the last one concerning a convergence to perfect screening and the caveat of adding just 1 stage to a screening process. Now, in the last, I'm going to take just 1 more minute. Now we're actually working on, we are done with the decision problem. We feel that we really squeezed this lemon, this bone dry. And now we are feeling comfortable going through a game. Okay, so now we're working on a screening game where you have 2 journals, 2 editors, and they need to decide how to adjust the screening process. And now you have these researchers that decide where to send, how to send their paper. Maybe go with this one first or the other one first, and so on. So now we're feeling comfortable going to a game. Hopefully we get good results and present it soon. Thank you.
Thank you, Dudu. Thank you. Questions?
I had a good time. That's fine.
I have one. So you focus. So is there a way to go the other direction and to, given the noise, try to design the best split of the best repartition on how many people to cut at every stage in the sequential screening?
Well, actually, that's a good question. I think that this will be most relevant to the follow-up study. I'm not sure. I don't know, but that's a good question actually. Because in this case, it's well connected to what we are doing now. Because once you fix noise, basically the screening process, and now you allow for the elements to start choosing where to go, so you get this result of actually varying the original distribution according to n. Okay, so I'm not sure, but yeah, I think it's a great question.
More questions? Okay. Then we thank Dudu again.
Thank you. This was fun. We should do this again next week.
2 weeks. 2 weeks. I stopped the recording.